So I will write the function for y direction for your reference. So it's dabba f xy. This is the image. Xy is the image. Xy is the image. Or dabba y is equal to epsilon limit 0 0 will be if now x will be if x will be remain constant, and it will be y plus epsilon naught epsilon and fxy divided by epsilon, right? So this will be continuous. Let me do the discrete approximation. We'll get double f. It's very simple, right? මහලුකු දෙයක් කරන්නේ නැහැ අතර. ඒක කරන්නේ මේ සාමාන්‍ය partial derivative definition එක අරගෙන ඒක හරවනවා මේ discrete form එකට. මොකද අපිට මේ continuous functions නැහැ නේ image එකක් ගත්තාම. මේ image එක pixel ගොඩක් තිබ්බහම මෙහෙම මේකේ මේ continuous functions කියලා මොකුත් නැහැ. මේ ඔක්කොම discrete pixels නේ තියෙන්නේ. 1 2 3 කියලා එහෙම නම් කරනවා. ඒක ඔක්කොම අපි කියන්නේ discrete digital signal digital function එක. එතකොට අපිට මේ continuous function නැත්නම් වැඩ කරන්න බෑ. So we convert the image into what you call a discrete way. So we have to have like a discrete approximation for this operation, right? So what we do is we have y dabba y. So what we do is this particular small increment is approximated to 1 pixel, right? Y plus 1. Sorry, not epsilon 1. Right? So that's the whole idea. It's the whole idea, right? Not a big. So here in this case, what will happen is, so we have y, we'll have x image, right? So we'll have x here, we'll have y here, we'll have the corresponding pixel, and what we'll do is we'll get the we'll get this y plus 1 is this pixel. So the difference between these two pixels. Similarly, we can do this for all the images, all the pixels, right? Clear? Any questions? I hope it's clear. So you can always unmute and ask questions, right? This is not one way, so you can always ask questions. Okay, now we'll see. Now here we have an image where there's edges in both directions. Yeah, so you can see edges of this particular tiger. There's horizontal edges as well as vertical edges, right? Now, if you look at this image, what image? So I will put 1 and 2, right? I will put 1 and 2 here. 1, 2 here. So can someone tell me which image shows changes with respect to x? Can someone just drop me a text in the chat box? Or remember, we are using this convention, right? We are using this convention, y and x. So the x is this direction, y is this direction. So which image shows?
Is it y?
No. I'm asking, the question is which shows the change with respect to x, which is 1 or 2? 1 or 2?
Second one.
Second one, okay. So yeah, that is correct. That is correct, right? So the catch here is, right? Yeah, there's an answer in the chat box also. That's also correct. So yeah, thanks. So idea is, so we get the, so in this case, if you want to get the change with respect to the y direction, it's going to be dabba xy over dabba y, right? So in this case, we saw how the direction change was happening here, right? So dabba fx over dabba y is in this direction, see? So our kernel, so now in this case, the whole idea is now we have the function, but the function is not going to help us in realizing this in a software, right? Now, after, I mean, whole point is now we can, not only for image processing or computer vision, wherever we have a function, whether it's a function to like represent some electronic circuit or a software, there should be a way for us to realize this, right? Realize this in the real world. How we can get this particular function into the real world. That is what we have to look at. So in this case, to realize this, you can see here easily, this is going to be the kernel format, right? Kernel format is going to be somewhat like this. So the by fx over by y is going to be something like this. So we can put, so we are trying to add two together. I mean, sorry, find the difference between two. No? So we can say -1 and 1. So this is the kernel. This is the what do you call a vertical edge direction kernel, right? Fundamental. Okay, this is not how you implement this fundamental. So, and also for dabba f y dabba x. Here, if you take, if you look at that, you saw that it was this direction. We are looking at the variation in x. So variation in x is going to be somewhat like this, right? It's going to be -1, 1. In both these cases, it can be other way around as well, or 1 - 1 here. So also it could be 1 - 1, or right. So both are correct. Both are correct. So right. So now once you submit this, so I will have another slide and explain this as an example. I'm going a bit fast. Sorry about that. To cover area, there's a lot to cover. I mean, there's 105 slides, right? Don't worry, we'll not be requiring all these slides. I mean, the most important part will be the edge direction. After that, I will try to quickly go through. Some corners as well, right? So edges basically will be 33 slides. We'll try to finish that off, and I will try, if there's time, I will try to go through some corners. Connotation also at the same time. This blobs part will completely disregard. Blobs part will completely disregard because that's not important, right? For you guys. So Harris connotation is where exactly we want to go. And there's another feature extraction method called SIFT. Any of you all have heard of SIFT? It's like what do you call? I mean, a scaled invariant feature transform, right? So basically, like a feature extraction method. We used to like this thing. If we don't have time to do that today, maybe I'll add a small recording on that. I think that's not necessary. But the problem is most of these things are quite old now, and we have to also keep in touch of new technologies as well, right? But already there in the world. Okay. Yeah. So I just wanted to add that this. So this is the kernel, right? So I think I'll get this right. Okay. So now I will try to add another slide here. and I will try to explain this kernel's operation because I'm trying to focus more on this edge part because that's the most critical part. That's where actually you all have to get the best understanding of. So yes. So if we take the direction of axis as x and y like this, okay, and so we know double I over double x function kernel is going to be realized like this. So I will put three these things. It's going to be 3 by 1 since it's 2 by 1 is not exactly what we use. Same thing, not going to be a problem. And double I over double y is going to be -1 0 1. So how this will operate is that uh, how this is going to operate is that, so imagine there's vertical edges, right? So it's a vertical edge. You can see this is dark, this is light. So once you send this kernel through this, you will be able to identify these vertical edges, right? Once this is submitted to this, you will be able to find uh, vertical edges will be emphasized, right? And at the same time, if you submit this to horizontal edges like this, right? Be dark and bright. It's bright. Horizontal edges will be, yeah, right. So why? You can see, right? When you submit this kernel here, if you are going to define this center, right? It's going to be a very dark value times -1 plus a bright one times -1. So you will see a quite distinction, right? There will be a variation. So then of course you will see this edge. So always remember the catch, right? Catch is that uh, the output will look like the curve. Right. Okay, so that's the whole idea. Now we'll go to the next slide. Okay, so now when you're trying to realize this, uh, we don't use small kernels, right? We don't use small kernels. The reason is, uh, you know, yeah. So the reason mainly is that small kernels are when you use small kernels to filter images, the resulting image can be noisy, right? So when you use small kernels to filter out images, the resulting image can be quite noisy. So to prevent that, we use these conventional 3 by 3 kernels. So basically, that's these are like you can remember when you were talking about neighborhood operations and we were talking about kernels. We discuss about different kernel types, right? We discussed that certain kernels have to have certain properties about a well-defined center and all these things, right? So another reason why we use these large kernels is that small kernels can be quite noisy, right? So and also here this is the private agitation. Sobel also you can see here. Uh, so here you can see there's more emphasis given to the center area, right? More emphasis given to the center area in the Sobel kernel. So that is the difference here. Let's see here that's um, more emphasis to the center area. Okay. Okay. Now we go to the next slide. Okay, now we'll talk about the image gradient, right? What this image gradient is. So, so if you look at, if you want to find the image gradient, now we discussed all this already. So we said earlier that the image gradient, right? The image gradient is basically what? So basically intensity. If you get the intensities of the image and find the gradient, that is basically that will basically give us the edges of the image, right? So the gradients. I mean, if you look at if you plot the first derivative of the image as a gradient, and the extremas of that image will give you the edges, right? So now if you look at this image, you can see. So there's two types of two variations, right? So you can see dabba f and dabba f over dabba x. This will give you what? This will give you the x direction gradient. And dabba f over dabba y will give you the y direction gradient, right? So if you look at something like this, I mean, image like this, right? So what do you think dabba f over dabba? So if you look at this particular image, and if I get dabba f for dabba x, what do you think? So once again, x, y, okay. What do you think here? What would dabba f for dabba x be? Can someone tell me? Dabba f for dabba x? 0, right? Why it's we are trying to get the we are trying to get the differentiation with respect to x in this direction. So no changes, right? Almost if you like take one line, there's going to be no change. Each of these lines are not going to have any changes. No changes along this scan line, no changes. So it's going to be 0. Right? Dabba f for dabba y. It's going to be what? It's going to have some value, right? It's not equal to 0. So so we can get something like this. This I think is something corresponding this image. Okay, some problem with the graphics anyway. Yeah. So here, of course, the answer is already given, right? Answer is already given. So here also dabba f over dabba x is not equal to 0, but dabba f over dabba y is equal to 0. And there can also be images like this, right? Yeah, you can see that if you look at this image, you can see both. If you look at any given time, there can be gradients. There's a variation in both x and y directions, right? Both variation is there in both x and y directions. So dabba f and dabba x, both in this case, of course, dabba f over dabba x is equals to as well as dabba f over dabba y. It's also not equal to 0. Okay. Now clear up to this point. So this is how we actually obtain the image gradients. Yeah. So we know this gradient point direction of most rapid increasing intensity. This is the definition. So so how does this direction relate to the direction of the edge? How does the direction of that we find here relate to the direction of the edge? What's the relationship between the edge variation and the direction of the edge? It's perpendicular, right? See, So the direction variation is in this direction. We are drawing our scan line in this direction, and we are finding the variation in this direction, but the edge is in this direction. See, it's perpendicular, right? It's perpendicular. See, so the answer is it's perpendicular. Okay. And also there's another parameter. So the edge gradient direction is given by this, right? So this, of course, you can keep in mind. So theta is basically this particular theta value. Given by tan inverse double f double y or double f double x. Okay. All right. So now there's another parameter, a metric that we use to figure out the strength of the gradient or the strength of the edge, right? So that is actually found by this equation. So you actually get double f magnitude is given by this one. Okay. This one, this equation. So you can basically look at the image strength of the edge. And you can actually define some sort of like a thresholding characteristic. Say, okay, if this particular double f magnitude, double f mag, the gradient magnitude is above this value, that's an edge. Because there can be intensity variations. Just because there's an intensity variation, that might not be an edge, right? So in this case, in this image, you can see there's an intensity variation along this axis, right? This particular direction or this direction. But just because there's an intensity variation, just because it's non-zero, doesn't mean that's an edge. Okay. So you can actually, you will have to figure out, first you will have to figure out, okay, whether there's an intensity variation. If there's no intensity variation, then there's no edge. That's clear. Basically, if there's no intensity variation, there's no edge. That's conclusion that you can come into in the first place, right? And also at the same time, you will have to figure out the magnitude of the gradient. If the gradient magnitude is if very strong, very large, right? Then of course you can say, okay, there's a possibility that this can be an edge. But if just because there is a non-zero gradient, we cannot conclude that there's an edge. I hope that is clear to you, right? Keep that in mind, right? So you can specify that. Now, so these are some applications that we can use, right? So basically what they're trying to do is they're trying to segment out this image of this bear out of this and then replace it in here. And so, and no, I think they're trying to segment out this one, these two images, and place them here and try to merge out, or you call this cloning. So here, and then the seamless cloning, what they do is they actually sort of like get them all in the same page. So we can, there's this paper, right? In SIGGRAPH. This is like a research done in 2003. You can read the paper if you want, right? So yeah. Now we'll look at the effect of noise in an image, right? Effect of noise in an image. So in this image, you can see there's a little bit of noise, right? You can see there's a little bit of noise in this image. Now, if we get the, what do you think, what happens once you get the differentiation of this image, right? What do you think, what will happen when you get the differentiation of this image? So, you get the differentiation of this image, when you come with the gradient, it will be like this, right? Now, in a case like this, it'll be very hard for us to find the edges, right? Very hard for us to find the edges when it's like this, right? So, I mean, we can't see any sharp variations. So you can see, so the intensity variation is happening here. Intensity variation is happening here. So you can see there's a slight shoot sort of thing here, but you can't differentiate this, right? How sort of this variation is happening, because there are spikes everywhere, right? Why is that? Why is this happening? Because all these noises, because we are plotting the gradients, right? So the differentiation of a function, regardless of the magnitude here, the differentiation of a function will give the gradient variation, right? So if you have a noise like this, how how regardless how small the amplitude is compared to this will be a gradient variation, right? From negative to positive and positive to negative, right? Here also it's going to be negative to positive, but here also there can be, if you zoom out this like this. So, I mean, in terms of the gradient, because he'll not be the gradient function will not be looking at how large the amplitude is. It will be just simply seeing, okay, if there's a gradient variation, where that is, right? So noises have gradients. Noises have gradient variations. Then of course you can't use this. Then what's the solution? What's the solution of this? So obvious solution, we have to smooth first, right? We have to blur out the image first. Blur the image first. And so this is the signal, noisy signal, right? So we use a Gaussian kernel. This G is Gaussian, so I will write that. I will write the steps. We have the get the image, right? And then we apply smoothing kernel. In this case, it's Gaussian, right? And then what you do? We have to smoothen the image with this Gaussian kernel. How do we smoothen the image with the Gaussian kernel? We do the convolution operation, right? Convolution operation. That means just multiplication of f and g, right? So we do the convolution operation of the image. That's simply smoothen the image of with the Gaussian kernel. Now you can see this image, the noise image that we had here. Once we have done the convolution operation with the smoothing kernel, basically, if we after we smoothen it out, we have a non-noisy image, right? The noise has been eliminated. Now what we can do? Now we can get the differentiation. Now we can find the derivative of Gaussian smoother version. So once you get the differentiation, there will be variation here, no noise, right? You can see if you look at the image like this, if you go along like this, there's no noise variations, right? See, the only variation in the gradient is here. It's going from negative to positive. That will be there. That spike will be there. Get it? Now you can see. Now you can see once you get the differentiation, you can find out this. Right? Clear? It's clear? Anyone who has questions at this point? This is basically the estimation operation. Right? It's basically the estimation operation. So, any questions up to this point? I mean, if you understand this, you guys are in a very good position to understand the remaining, because once you understand one basic feature, it's very easy to plug it into other areas. So it's very much similar. So we find out a function and then try to figure this out. Right? Now, if you look at these functions, so you know that so in what we did here was we did the convolution operation. We did, then we did the convolution operation with the Gaussian filter, and then we did the differentiation. But you all know the convolution operation is linear. It's a linear operation, right? At the same time, the differentiation operation is also linear operation. So whenever there are linear operations, they are interchangeable, right? So basically, if you have two linear operations, right, differentiation and convolution, if both are linear, then those are interchangeable. So what you can do is you can interchange those and do it accordingly. That means you can get the differentiation first and then do the denoising or the convolution, right? That's what we are doing here. So what we are doing is we are getting the differentiation here, right? As you can see, I mean, this is definitely not the result. It's going to be a noisy result, somewhat what we got here, right? And once you do the once you do the convolution operation of that, you are supposed to get this, right? So this particular feature is there because of this particular function, that is linear operations are interchangeable. Okay, so yeah. So I hope that is clear. Yeah, that's all. Yeah, now if you find the derivative of Gaussian, so I think you all might have heard of the derivative of Gaussian derivative of Gaussian, and Laplace of Gaussian. These are like field types. Laplace of Gaussian is also like where you find out edges at the same time with the grid. So sharpening the image with this thing. Once again, same, we can find the derivative of the Gaussian, right? So as I said earlier, yeah. So can someone tell me which one finds horizontal vertical edges? One or two? Find this out. One or two? So okay, small mistake, not mistake, convention issue. We'll take this as iterations. Because we are using this convention. So this will find vertical edges, right? So this will find horizontal edges. So you can see here, this is the derivative of Gaussian function. You can see it's a 3D function. So here you can see there's intensity variation in two extremes, white and black. Similarly here also. So you can see it sort of resonates with, once you plot the filter, it sort of resonates with the image, with that, right? You can see the local maximas and minimas correspond with the filters plot. See? So you can see now, obviously you can see if you send this through, it will find out vertical edges, right? Vertical edges like this, because that's where this, because the filter is varying in this direction, so the edges will be in the perpendicular direction, right? similarly here also, right? So you can see here if I get my spotlight, see the vertical edges, filter variation is happening from here to here. So edge will be perpendicular, right? Here also, filter variation happening from here to here. I mean, intensity variation. So edge will be from here to here, right? Okay, so I hope that is clear. Yeah. So are these filters separable? Are these filters separable? What do you think? We discussed this already. Yeah, it is, right? They are separable. Right. So here now we move forward. They are talking about the proof of separability of the Gaussian filter. So if you want to prove it, if you want to prove the Gaussian filter is separable, so you can see here. So I'm not going to this basically proof of Gaussian filter separability. You can see what we are trying to do is we are trying to segment this out. So you can write this as 1 over 2 pi sigma squared. It's going to be e to the power x squared, and write this as 3 functions, right? E to the power x squared. So I will write this as minus squared over 2 sigma squared, and then e to the power minus y squared over 2 sigma squared, right? So basically you can separate this and you can write them as 2 separate functions in the bidirectional expression, right? So this is the separability proof, right? So yeah, so they can write this as well. Y x, right? Great. So guys, sorry once again. I think our time for this is also ending. So sorry about this. Anyway, this will be the last time that you'll have login, I guess. Is that the case? Yeah. So we will take a small 5-minute break as well. You can like drink some water and come. So and then we'll start once again at in 5 minutes time. I will keep the meeting ended. I'm not going to start it. So you join the meeting in like say at it's 9:54, right? 9:54, and then at that time I start the meeting and we'll continue until the end. Okay. Right. We'll see. We'll meet in like another 5 minutes time.